Hello. I would like to thank organize. Although I'm organizer, but I also thank for the other organizer for giving me this opportunity. But although, in spite of this nice opportunity, I would like to. I really wanted to present some other new work, but I didn't have time. So that's why you cannot find my title because I couldn't decide in the last moment. But in the end, I decided to present the old work. But this work is actually also very interesting. So this I will talk about basically multipartite entanglement and measure. This work originally with Vinay here in Gyeong University and Joydeep Kumar Basak from the GIST. And recently, in the last summer, we also do the follow project with also Byung-jun and here Kwon Bin-gu. He is the student in the undergraduate student of the Gyeong University. This is kind of part of the internship program. But here I add just one slide of this result, but it's interesting. So motivation. Actually, Kim also asked me, why am I studying this multipartite entanglement entropy? There could be many motivations. At least for me, I'm interested in the multi-boundary wormhole. And then you can ask, what is the holographic dual state of the multi-boundary wormhole? So we know that the dual state of the black hole. And the dual state is a Sommerfeld double. And then the multi-boundary wormhole, there is many suggestions. You may suggest, oh, maybe GHG or W or etc. But you might ask also, is there multi-boundary wormhole in the gravity? I don't know 4D or 5D how to explicitly construct it. Maybe there, I'm sure there is a way, but I'm not expert on that. But at least 3D gravity, I know how to explicitly construct. So at least 3D, at least pure gravity, you can construct explicitly this multi-boundary wormhole by quotienting this time slice of the ADS3. So if you quotient with this one, and then you have a black hole, but if you quotient further, then you have 3 boundary wormhole, and if you quotienting more, you can have more and more boundary. So, black hole case, we know that black hole is a thermal state, and then you can purify the thermal state, and then you have a Sommerfeld double state. And then you can take an infinite temperature limit where beta is 0. Then you have this state. This is nothing but maximally entangled state. So this is one we know well for the black hole case. Now, multi-boundary wormhole, it's natural to ask what is generalization of Sommerfeld double. Now it's a little bit, we don't know what to do. It's a very, because now you have 3 CFT. If there exists a boundary CFT, then you have 3 CFT. And if there is 2, it's very easy. You can have like a E and a EN. And then you can, but there are 3. Maybe you can guess. What about the 3, not the EN cross EN, but the EN cross EN cross EN? Maybe it's a good choice, a good guess, but you are not sure whether it's really due to this black hole. Maybe Sommerfeld double is too difficult because you also interest temperature. And in principle, you can have a different temperature in each boundary. So it's a bit another confusion. So why don't we take first beta equals 0 case? Then the natural question is what is generalization of the maximally entangled state? That question is also, as far as I know, maybe some other quantum expert in the quantum information people maybe know, but I don't know what is the consensus on this maximally entangled state for the multipartite case. So because of the definition, so for the introduce this multipartite integral state, then let's first go to the best state, because this is the simplest maximally integral state with the smallest qubit. So it's a good example. So we have best state. What is property of best state? If you trace out one of the own party, you have two qubit, and if you trace out the one, the resulting reduced dense matrix is maximally mixed state. As you know, this is just proportional to the reduced dense matrix is proportional to the identity. And then we know that this maximally mixed state saturates this von Neumann entropy. And then this is a good kind of clue to generalize this the bipartite entanglement entropy to the multipartite entanglement entropy. So now you can ask how to generalize to the multipartite case. So this is quite interesting, and many people, I believe that in the HepTH people also, they are also have the same motivation to me, and then they trying to generalize it. Not only that, but also some mathematicians, they have their own way to generalize multipartite entanglement entropy. And then also recently, Korean government also announced some research grant for this multipartite entanglement entropy. But for them, they are not interested in this theoretical approach, but they are more interested in the multipartite, I mean, how to construct and control the multipartite entangled qubit. So it's a slightly different point of view, but anyway. So before going to the generalize, you can ask, we know that several multipartite entangled state. One is GHG and the W state. Of course, they are multipartite entangled, but maybe which you have to ask which one is a more generalization of the Bell state. Bell state is was very special because it saturates it's a reduced density matrix saturate the von Neumann entropy. So we know that this Bell state is very special, but here there are not only GHDW, and there could be many other multipartite entangled state, but there must be one very special state which you can say that it's maximally multipartite entangled. To answer this question, we need something more. I mean, we need first several concepts. First, we have to generalize this maximally entangled state to the maximally multi-entangled state. So we have not only two, but many. And we need also some measure. So in the bipartite case, we have this von Neumann entropy play role to distinguish which one is maximally mixed or maximally entangled state. Here, multipartite case, what is the good measure to say that some state is maximally multi-entangled state? So probably starting point should be define some new measure to guide the what is the maximally multipartite entangled state. So our answer, upshot is our proposal is this, we define some kind of L entropy. We call it the latent entropy. And then, this is nothing but the difference between if you say that this is two subsystems A and B, and then this is the difference between the minimum of entropy of A and B, and multiply twice, and this is the reflected entropy, A and B. Probably all of you know what is the entropy of the SA. So I will shortly explain what is reflected entropy. reflected entropy is you starting from some mixed state, log AB. It need not to be pure state. It's a mixed state. And then you can purify this mixed state. And then there would be many ways to purify this mixed state. So I choose a canonical purification. So basically, you just using the Smith decomposition, you just square root of this kind of Smith decomposition. So that's why I'm using the square root. And then you trace out, for example, BB star, and then calculate this von Neumann entropy of this reduced dense matrix of the AA star, and then that gives this define the reflected entropy. So the reason why we choose this combination is that this reflected entropy has this inequality. So we choose this inequality. I mean, using this upper bound. Using this upper bound, we define the difference between the upper bound and the reflected entropy, and define the L entropy. And in general M-party system, we calculate first all possible choice of the two subparty. Let's say, for example, I choose the A1, A2, and then calculate the reduced dense matrix of the A1, A2, and then calculate the L entropy. And then also you can choose the A1, A3, and then calculate the L entropy, etc. You calculate all possible L entropy and then multiply them. The reason why you multiply them is that if some of them, you can see later, but if some of them become zero, then all of them become zero, then that zero in this measure, zero over this measure means that it's a separable state. I will explain soon. So we define this L entropy. Anyone can define your own measure. In fact, there are many proposals for this measure for the multipartite entanglement entropy. But there must be some criteria that such kind of measure is reasonable to explain this multipartite entanglement. First of all, first criteria is very natural. If a state is fully separable or biseparable, whatever, if it's separable, it's reasonable to say the measure is zero. Zero means that it's separable. You can imagine also von Neumann entropy become zero because of some separable case. But also non-biseparable case, it should be non-zero. So that if it's zero, then it's separable, but it's not zero, then it's not separable. So it's a very reasonable and trivial criteria. And the third one is local. It should be under the invariant under the local unitary transformation. So you have each system, and then if you take perform the local unitary, local means you can just act on the unitary transformation on each subsystem separately, then the measure is invariant. It's reasonable. And then the most non-trivial and difficult to prove is this non-increasing under the LOCC, local operation and the classical communication. So this is somewhat difficult to prove. So actually, every measure, the proposal for this multipartite entanglement entropy satisfy these three. The first one is a little bit difficult to prove it, even. So, but because we use this reflected entropy, that's actually one purpose. One reason why we choose this reflected entropy, because this criteria can be proved. So that our average L entropy satisfies this criteria. Now this our measure has some inequality. Also, there is a bound of this L entropy. So bound you can, if each subsystem dimension is D, for simplicity, you can calculate any case, but for simplicity, let's say each dimension of the subsystem is D, then the bound of this average entropy is 2 log D. So depending on the number of subsystem and the dimension and etc. So depending on that, this inequality can be saturated or cannot be saturated. So for example, 3-party case, if you have a 3 subsystem, and then average the L entropy is not bounded by 2 log D, but the log D, which is the value of the L entropy value of the GHG. In some sense, maybe GHG is a maximally multi-entangled state of the tripartite system. However, it's not saturate the general bound. Then it's very natural to ask, in general, which state saturates this bound? Such a state should be very special, and it's analogous to the Bell state. So we can ask. It turned out that it's already known. It's well studied in the quantum information and some mathematics. And then there is a K-uniform state, and this state saturates the bound of our entropy. So what is a K-uniform state? It's very simple. For example, this K, let's say 2 uniform state. 2 uniform state is that if you choose any 2 subsystem, for example, A1, A2, and then its reduced density matrix is maximally mixed state, then we call it's a 2 uniform state. If you say K uniform, if you choose any K number of subsystem, all possible K choice of the K subsystem is a maximally mixed state, then that state is a K uniform state. This is you can easily see that this is a nice mathematical problem. What kind of state satisfy this condition? So mathematician try, and then you can easily calculate that this K uniform state saturate the L entropy of the K uniform state is 2 log D. It's a very simple calculation because the density, reduced density matrix is identity, and the calculation is straightforward. Now, if
I start with some qubits, some n qubits, is it obvious that such a state has to exist?
Yeah, so that's what I'm about to say. So, when I learn the mathematics, they usually start prove the first thing they prove is whether existence and then uniqueness. So there are several papers when it exists, when it does not exist. So there is a condition. So there is an n-party system, and then you ask whether the K uniform state exists or not. So it exists only if K is less than n over 2 flow over n over 2. So for example, tripartite case, if you ask a 2 uniform state, so tripartite is 3, and then this flow is 1. So K equal 1 satisfies this condition, but the K equal 2 does not satisfy this equation. So that's why tripartite case, there is no 2 uniform state. So that's why GHD set, even though it's maximum L entropy, but it's not the general, the maximum, L entropy, 2 log D. It's not 2 log D, but the log D. And the one caveat is that this is equality case. This is the necessary condition, but if there is it's a strict inequality case, probably I believe it's proven. But the equality case, it's not fully proven. there are several cases which is still open question, whether they exist or not. So example of K uniform state as follows. For example, this bell state is one uniform state. One uniform state means that if you choose the one party and trace out the rest of them, it's a maximally mixed state. We know that if bell state, if you trace out the one of them, it's a maximally mixed. So this is a natural one uniform state. And then there are, for example, this is a two uniform state, meaning that if this is a five party, so 5 over 2, each flow is 2, and then 2 equal 2, but even though it's equality, so but you can easily find such kind of state. So this is a two uniform state, meaning that you have a 5 qubit, and then if you choose 1 and 2 and trace out the rest of them, then reduced density matrix is identity. You can easily prove it, or any other choice will give the identity. And our measure, in fact, you remember that our measure, this L entropy, choose two subsystems. And then if you think a little bit more, our measure only characterize two uniform states. And then you can also easily convince that K uniform state is a two uniform state. Because if you choose a K subsystem, it's the density matrix is maximally mixed. If you trace further to have two subsystems, then it's the reduced density matrix still identity. So that's why K uniform state, which is K is greater or equal to 2 case, always a two uniform state. So our measure capture the K uniform state, which is larger than K is larger than 2, but cannot distinguish two uniform state from the three uniform or four uniform, etc. And last summer, we trying to generalize our measure to capture those K uniform states. How to distinguish two uniform from the three uniform or four uniform, so that instead of choose 2, but we choose 4, and then trace out the rest of them, reduce, and then also now you do the canonical purification, and then choose the half of them, and then calculate the von Neumann entropy, and then this give this reflected entropy, and calculate this error entropy, some generalized error entropy for the four-party case. And then it turned out that it can capture the, for example, in this case, four uniform state, etc. So I didn't push given more data for that, but I hopefully that we can report it soon. But the next natural question is, so far we discussed the exact maximally multi-entangled state. But for us, it's very natural to ask the L entropy of the typical state. So von Neumann entropy of the typical state, or entanglement of the typical state or random state, give this page curve. So you can, it's very natural to ask the two uniform state is whether it's it's already mixed. So here I would like to say that this typical state is close to the maximally entangled state. So that in this case, if you trace out, so this line is the maximally entangled state line. So the typical state is close to that, but after the page time, it's already far away from the maximally mixed state. So now question is whether this our measure, from our measure, whether this typical state is close to this maximally multi-entangled state or not. So to answer that, we calculate several like analytic calculation and the numerical calculation. Thanks to this paper, we could calculate the reflected entropy of the typical state by using the random matrix theory, and then this is the result. And then, for example, the n-party case, which n is larger than or equal to the 5 case, we could show that the L entropy of this pipe or n-party case is almost saturate the maximum value. That means when n is greater than or equal to 5, it's almost maximally multi-integer state. And there is also, of course, there is correction. And then we also confirm that numerically, this is a blue line is a numerical calculation, meaning that you just calculate numerically calculate the qubit and then calculate the L entropy and then compare with this analytic result, and then it's almost close each other. And then as you expect, 3-party case, even random state is not close to the maximally multi-integer state, because if you follow this analytic calculation, the reading piece is 1/2, which is much smaller than the usual GHG, and also it's smaller than 2 log D. So this is trivial. But the most non-trivial case is 4-party case. 3-party, the random state is not the maximally multi-integer state. More than 5, it's maximal. But the 4-party case is a little bit unclear, because here our measure captured the 2 uniform state. So you remember that the inequality for the existence of the k uniform state. According to that, this 4/2 flow is equal to this k, the 2. So it's a little bit unclear. Also, the random matrix calculation, in the random matrix calculation, there are 2 saddles. So analytic calculation show that there are 2 saddles. So one saddle is followed this one, which is give the maximum value. There exists another saddle, which is smaller than 2 log D maximum. So analytic calculation, you cannot say that which saddle really you have, which saddle you will really have. So we calculate this numerical calculation for each dimension. And then it turned out that they follow the lower case. So the lower saddle. So we could confirm that 4-party case random state is not 2 uniform state. So this is related to this one. So in the end, if there are 4-party, we choose the 2-party among the 4. So it's close to this page time. So in page time, it's a little bit, as you see, there is some deviation from the maximally mixed state. So this is in the end, this is the origin of this problem.
Maybe I missed it, but how come you find the random state?
I didn't mention, just say. Practically, the random state is that you define for example, first some qubit, and then coefficient is some random number. Yeah, just a typical, yeah, Gaussian random, and then normalize. So far, we discussed no temperature. So it's important to how to introduce temperature, because in the end we are interested in the black hole, and the black hole has temperature. K uniform state is more like a maximally mixed, like a maximally integer state, which beta is 0 or infinite temperature. So we have to introduce temperature, but this bipartite case, it's very easy to introduce temperature because you just add the Boltzmann factor, and that's all. It's very easy. However, Now you have a 3 or 4 and more party. And then we know that what is maximally multi-entangled state, but how can we introduce temperature? And this temperature in general is not one temperature. It could be many temperatures because each boundary could have different temperature. So it's a very confusing part. So this is still we couldn't have a final answer, but we have some suggestion. First, we found a very nice paper from the Japan, Sugiura and Shimizu, 2013. And then this is a very, their philosophy is very close to a Sommerfeld double, but it's quite different. So they first choose the random state. Random state is the same as like a random coefficient. And then you act this Boltzmann factor. It looks almost same, but yeah, Boltzmann factor to this random state, and they define the thermal pure quantum state, they call it. From this perspective, this is very close to the Maldacena-Kolkolov pure state. It's almost same law, but the only difference is that Maldacena-Kolkolov is this is a very simple state, which is 0001 or some any simple choice, but this is a random state. And then their claim is that if you want to calculate the thermal expectation value of some operator, then instead of calculate this one, this TPQ state give the nice approximation to this thermal correlation function. This is also very similar to the Maldacena-Kolkolov pure state. But the difference from the Maldacena and this here is that because the randomness, so in SYK case, it's okay to choose any simple state because there is a random coupling constant and this play role of some random this average. But here, this suggestion can be work in any other condensed matter system. So in condensed matter system, you don't always have this random coupling constant, like Ising model or this one. Then this random state, by the way, this average is over this random state, give the nice answer. So this is a kind of, you can say that this is a good approximation of the thermal state. And this is very nice. But there is a big difference between from the Sommerfeld double state. First of all, Sommerfeld double state is it's equality. It's not approximation. This is because Sommerfeld double state is a purification of the thermal density matrix. So at least this is identity. And then you need doubling. So your Hilbert space is double. But the TPQ state in the original paper, they emphasize that they don't double. Of course, it's an advantage because you want to approximate some system, but if you double it, sometimes you cannot calculate because the Hilbert size is too large than your classical computer cannot calculate it. But if without doubling, if you calculate efficiently, then it's nice. So for them, it's very nice without doubling. But for us, there is some problem because we are interested in the black hole. If you are interested in the correlation function on the one side, it's okay, no problem. You can use the TPQ state without doubling. Maybe that is much better because it's your computer can calculate. However, if I want to calculate this correlation function between the left and right, now without doubling, how can I consider these two operators? That is first very confusing. And then there are some practical reasons, but I will just skip some other caveat. So in our proposal for this kind of multi-boundary wormhole, we change it. It's just a small change, but we double the we consider the copy of the Hilbert space, although it increases Hilbert size, but it's good to understand the multi-boundary wormhole. And then act this Boltzmann factor on the each Hilbert space. So this is the first proposal. It's natural. And then you can also prove that this state, if you do this random average, it gives this right-hand side. It's a very simple calculation. If you just random average, and then you can obtain the right-hand side. This is just kind of undergraduate calculation. And then it's very tempting to say that this state, which I just construct, due to this multi-boundary wormhole. However, it's not. At first time, I thought when I obtain it and I like it, but in the end, I found some problem, so I was very confused. So let me explain the problem. So if you calculate the correlation function on the one side, one boundary, like O1, O2 located on one boundary of the CFT, then no problem. Even this averaging without any numerical calculation, you can just prove that under this average, it represents this one. So it's nice. However, as I said, we want to calculate the correlation function between the different boundary. Now you can repeat the same calculation. And then what you obtain is a factorized correlation function. In particular, this is a thermal one-point function. So it's kind of disconnected. This is not what we want. We want to, if geometry is connected, then there would be some, I'm not sure always, that is actually our question, but usually you can have a geodesic distance, geodesic between the O1 and O2 that gives an approximation of the two-point function. And if a geodesic exists, then this correlation, you will have a connected some two-point function, but the result is not. So this factorization is really a problem, and then at that time we are a bit, because the previous result is too good, so we don't want to accept that this is wrong. But we found some interesting idea. So this will contradict. So like even black hole case, you don't have to go to this multi-boundary one. Even black hole case, you know that this should be, the correlation function should not be factorized, but here it's a factorized. It looks like a contradiction, but this contradiction actually appear in the in our black hole information paradox. So when we say there is a black hole and when we consider this correlation function, etc., the operator is state dependent, whatever it means. So I mean, here, for example, one in our understanding for this operator state dependent is that when you construct the O1 from the O2, this depends on the state of the state, means this microstate of the black hole. So it's not the state, the O1 and O2 is not, you cannot define state independently. However, here, when I calculate this O1 and O2, it's a state independent. Because when I do this random average over the coefficient of this state, it's nothing to do with this O1 and O2. So that's why it's factorized. So probably this is this is a fault of our proposal. So probably, so we're trying to find the alternative way. So we ask, how can we define the state-dependent operator in O1 and O2? So I will give you a simple example, and we later I have some slide for the multi-boundary case, but I always have difficulty in explaining people because I realize that people easily decouple when I explain that one. But if you wonder the procedure, please let me know. So now you have here black hole bipartite case is straightforward. You have a random state, and then you have two bipartite. You consider like a bipartite case, and then you can do the Schmidt decomposition. This is a standard, and then somehow now you have a Hamiltonian original. Let's say in our case, let's say consider like a SYK Hamiltonian. Given SYK Hamiltonian, you can define the energy eigenstate and each energy. So given Hamiltonian, Hamiltonian is given, and then you can find the energy eigenstate and each energy. And then we can define the unitary operator, which map from this Schmidt basis to the energy eigenstate. And then we define this unitary transformation of Hamiltonian. So basically, we change it to this E basis to the sigma basis, etc. And then we define multipartite typical state by acting this Hamiltonian, not the original Hamiltonian, but this Hamiltonian, and define this way. And then this alpha, you have to choose. But here, in general, how we define this alpha is that we first calculate the reduced density matrix of each party, and then compare to the relative entropy between the thermal state that we want to have, like we target some temperature beta thermal state, and this state, and then trying to minimize the relative entropy. And then in this black hole case, it's easy to calculate this temperature is beta is 2 alpha. So this is basically beta over 2, which we know well. And then you can easily see that this state is nothing but a Sommerfeld double state. Now, when you define the operator O, you also transform this operator O by this unitary transformation. So you define the okay. So you define you act on this unitary operator on the operator O, define the OL, and the unitary U on the O, and define OR. And then in this way, this U coming from this Schmidt random state, and the random state encoded in this unitary operator, and then that's why this operator is now state dependent. And then you can also calculate this one. So for the right side operator, and then you can easily just exactly show that it gives the thermal expectation value. Now the most non-trivial thing is the OL and the OR, and then you can also easily prove that because of this unitary transformation, this gives the expected result, the correlation between the left and right. So bipartite case is very easy, and then you can actually generalize to the multipartite case. It's the same thing, so I will just skip the detail. But the procedure is the same using the Schmidt decomposition, but you cannot have a Schmidt decomposition in the multipartite case. But here I consider the K party and the rest of them and the Schmidt decomposition, and then define the U and etc. And then you can also define this temperature, etc. So upshot, I will just show you the result. So when you define this operator, state-dependent operator O, and I also using some unitary transformation which encodes this state information. And then, for example, here, one thing is that now you are not sure whether this state gives the expected result. So here you can check that here this is a 5-party case. So you have 5 boundary. And the SYK, this 3 qubit means you have n equals 6 SYK. Each boundary has n equals 6 SYK. And this is, in total, it's n equals 30 SYK. It's actually limit of our computation in the classical computer. Or you can do a little bit more, but it's almost. And then here this graph means that you calculate the reduced density matrix of the one subsystem. And then whether you can ask whether it close to the thermal system or not. And then this compares. So this is relative entropy between the thermal density matrix and this reduced density matrix, and it's very close to each other, etc. So we confirm that this work well means that this gives the expected result. But however, there is some caveat that here, strictly speaking, what we impose is one thermal uniform state, meaning that if you trace if you choose the one subsystem and trace out the rest of them, it gives the thermal state. This is what we want. But I have to also check that instead of just one state, but if you choose the 2 subsystems and then trace the rest of them, whether it's also the product of the thermal state or not. This kind of question we will check soon. And then let's a little bit explain the future work. So we defined this multipartite thermal pure quantum state, MTPQ state. And then we hope that this is due to the multi-boundary wormhole. We don't have strong evidence yet because it's usually difficult to calculate correlation function. Even numerically, maybe you can calculate, but even though it's n is small, but you can calculate. But even gravity calculation, it's not easy. For example, you have to calculate a 5-boundary wormhole and the geodesic distance between boundary to boundary. It's non-trivial. We try, but there must be an answer, but it's difficult. But we hope that we understand better. And we characterize this K uniform state. And this K uniform state can be used various applications. So, for example, nowadays quantum technology is very important. So, quantum secret sharing, or it can be used in quantum cryptography because you have a multi-subsystem. For example, 3 uniform states. Let's say if you have a 3 uniform state and then you have like a 7 subsystem, and then if you two subsystems meet each other and share the information, but they cannot extract any useful information, but because the reduced density matrix of the 2 is a maximally mixed state. At least for 3 uniform states, 4 parties should meet each other or communicate to get the useful information. So that's why this is very useful to the quantum cryptography, probably. And then this typical state can be studied for the black hole microstate. This is actually also hope. And another thing is this typical state can be used in the quantum simulation because you can ask how can we simulate a black hole in the quantum computer? So you need some pure state in the quantum computer. Of course, you can purify Sommerfeld double. You may answer Sommerfeld double. But how to prepare Sommerfeld double state quantum computer? Classical computer, it's easy because you can diagonalize Hamiltonian and then you just plug into the coefficient, that's all. But the real quantum computer, it's difficult. However, typical state, we know how to generate the random state. And then we know, actually, it's a little bit difficult, but we need to act on the Boltzmann factor. but there is a way to act a Boltzmann factor in the quantum algorithm. So that is a very good, maybe some practical, there could be some practical application. And thank you for listening.
Questions? I don't know very much about these multi-boundary wormhole geometries. Do they only have one temperature associated to them?
No, need not, because depending on the quotienting, here very early time at least to me, this is the only way that I know to construct the multi-boundary wormhole. Maybe some other people know better. So depending on how you quotient, each boundary could have different horizon size and the temperature different. So it's to me, it's very difficult to have the same temperature. There is a way, but you mean the quantum state of this multi-boundary?
You have system that's in contact with different heat beds of different temperature, basically, right? So there will be sort of dynamical situation of, if you put, say, additional matter field, for example, things that can actually propagate, and the quantum state will not be static. It will not be analog of hot rocking, for example.
Maybe, but here this is a pure gravity case. So if you're adding matter, I don't know. Probably yes, that you're right. But another, I mean, here we construct this in the end I described this some numerical calculation. That calculation, of course, that doesn't mean that it's a holographic dual, but that state showing that each subsystem has close to the thermal state. For example, this, I'm not sure which one is good. So this is a 5-party case. Here I define the same temperature, but here we can calculate also different calculation. So overall, it's a static situation for now, but you can define this way. At least you can define, but I don't know what interpretation of that. So maybe as the time passes, maybe temperature could be different. That I didn't check. Maybe it's a good approach to do.
Okay, could you back to the page curve? Okay, could you back to the page curves? Okay, here. Can you apply the method to before the page curve? Okay, and what happens? Can you make some comment?
Yeah, this is actually this slide. So whether you choose here page curve here. Now question is here you choose the random state,
right?
And then you consider the bipartite system, and then change the dimension. So this is x-axis. So here I didn't choose this x-axis, but instead of that, I kind of, now you have multipartite. There are many dimensions. So here I change the dimension of C, dc. So dA, dB is fixed, but the dc is increasing. So it's not really same as a page curve, but basically it's just the rest one is increase. So this is kind of curve, but now what you really need is fix the whole dimension.
Right.
But we can do that. Yeah.
I see.
Yeah, I didn't.
Okay. Also, can you check up the change of the temperature, and then what happens? You have the maximum point of the page curve, and the shift or the fixed.
For example, if in page curve case, if beta is larger and larger, so
Right.
you go to the more and more ground state, so that maybe it goes to more and more, because beta equals 0 is just a ground state, then ground state is just a separable state, so I believe that it's just this 0. So probably if you increase the beta, then this curve will go down.
Okay. Thanks a lot.
So your resolution of how you get a non-factorized answer is that you define operators in a way which depends on the states.
Yeah, that's right.
But I could have also calculated just the partition function, like in Euclidean gravity, I just calculate that path integral. So then, that itself would have an answer which is not factorized because it's a wormhole, right? So is there an understanding of that in terms of states?
It's a very good question, but we didn't have time to focus on that. But yeah, we can. It's possible to think of that, but first of all, my final answer is I don't know. But if I try to answer that.
Because now you don't have any operator insertions, just
No.
a partition function.
Yeah. So, for example, because it's a pure state, so that you can say that the overlap, it's normalized. So I don't know how to calculate partition function from here. So basically, I don't know. And then another thing is that, can it be trying to think it as some microstate of black hole? Because black hole has many microstates, so this random state, the random choice is kind of a microstate. But this is a hope anyway. And then, so each microstate, can you calculate the partition function from that each microstate?
Well, each microstate is not supposed to be degenerate. So I think there is nothing. Just one state. So it's one term in the partition function.
Maybe I have one kind of suggestion, although I'm not sure, because now you do this here. I did not explain well, but when I define the typical state and etc. So here we choose the one random state, and then e to the minus beta h, and then each temperature you kind of generate many such a state. At some point, because Hilbert size is finite, at some point there will be they are linearly dependent. So there will be linear independent set. So maybe that can be.
Oh, I see.
But I'm not sure.
Interesting.
Yeah.
Thank you.
If there are no more questions, let's thank the speaker again.